Hi, I'm George Magklaras. In this video, I shall be talking about Linux control groups. It's not a new technology, but in light of reviewing the Red Hat Enterprise Linux version 7 and the resource management with Linux containers, one of the key technologies that containers use is that of control groups. Therefore, I'm making this video. If you are a sysadmin or you are in the DevOps arena, you have seen a situation like the one in the picture here, where a pretty hefty system, in this particular case a 32 core quarters of terabyte of RAM system, can be easily overwhelmed by heavy and asymmetric utilization. Of course, one way to solve this situation is to apply U-limits, but there are smarter ways that help you tag the processes and therefore make a more refined resource management model, and that is a Linux control group or cgroup. So essentially, a cgroup is a way to administer a number of resources and set resource limits to them by using certain resource controllers or cgroup subsystems as they are called. So you can administer CPU, memory, network bandwidth, and block I/O resources amongst a hierarchy of processes. A cgroup hierarchy is something that you have to get used to if you are not familiar with that concept before. As I said, cgroups is not a new concept, but essentially very few system administrators actually employ it in production environments so far. So it gets certain getting used to before you are confident to actually deploy them in production. So let's go ahead and see how systemd, the core tool, employs a cgroup hierarchy. If you are not familiar with systemd, you can watch a video that I made that explains its basic usage. The link will or should pop out on your screen right now. Please make sure you review that video if and only if you are not familiar with systemd, because you'll need that knowledge to get further into this particular video. So, going back to the cgroup hierarchies, we have, first of all, slices. Slices which are actually underlined here, and of course they are in italics, because in themselves they don't actually contain any processes, but they provide the blueprint for organizing a hierarchy around processes. And in particular, a slice might contain a service or a scope. A service is of course a hierarchically group ordered set of processes that actually refers to system services or things that are started via systemd via permanent unit files. A scope is a little bit different, is a hierarchy of processes that can actually start or create processes dynamically. So we're talking about transient processes, things like user sessions or virtual machines that might fire up, or containers outside the boot time. This will be organized in a scope, which of course will be contained inside a slice. Slices, the blueprints for actually holding a hierarchy of processes, they are named in a way that can hint the hierarchy. So for example, we can see here that the slice name dash instance should be a child of name.slice. And of course, the dash.slice is the root slice. There are 4 default slices that you should see easily on most systems that employ cgroups. Of course, the root slice, which is the mother of all slices, sitting at the very top of the cgroup tree. And then we have 3 other categories of slices. The system.slice, which should by default contain all system services, so things like the Bluetooth service, the HTTPD service, the SSH daemons, should actually go by default under the system.slice. The user slice is of course the default place for all user sessions. So processes like SSHD in some systems, and the graphics display manager related processes should actually appear under user.slices. And finally, we might have a specific slice for virtual machines and containers, the machine.slice. If you don't understand what all these things mean and it seems difficult, don't worry, there will be plenty of examples in this video to demonstrate the concepts. Before we go on the command line on RHEL 7 terminal, here is a review of the key group commands, the most important cgroup commands that we're going to use. At the very top, we're going to see the systemd cgls and the systemd cgtop. These are two commands that one may employ to in order to display the hierarchy, the cgroup hierarchy of processes, in particular the first one, the systemd cgls. And the systemd -cgtop is of course the equivalent of top, but cgroup oriented. So you can see, for example, how much CPU and how much RAM is occupied by a particular slice. The systemd run -run is a very useful command that actually illustrates how we can start transient processes and create scopes. Of course, the systemctl command, and in particular the systemctl set property, which is actually used to apply the limits to a cgroup, a hierarchy of processes controlled by a cgroup. So this is the command that you use to use a particular cgroup subcontroller to limit CPU, memory, bandwidth, and a number of other resources. Okay, so let's go now to the command line. Here we have a ready configured RHEL 7 system, and we are going to start by actually demonstrating the hierarchy, the cgroup hierarchy of processes. Traditionally, you would do something like top or PS3 to actually view the tree of processes running in a system. But if you want to see the control groups, what you should do is invoke the systemcgls. And as you can see, systemd -cgls gives you the cgroup hierarchy of processes. We start, of course, by the root slice, which is, of course, the systemd process itself. And then we see the various different slices, default slices that we talked about earlier on in the slide. So the user slice in this particular case might contain a sub-slice. So user-1000.slice should be a child of user.slice, and in itself it might create a user session, and the user session itself creates a number of processes associated with a user activity. In this particular case, this slice represents me logging in into the system. So this is my shell, this is the secure shell daemon processes that are actually forked to handle the shell, and this is the command that I just executed to illustrate the systemd cgls. On the system.slice, we can actually see a number of services, pretty much like we see services on a systemv based older system. So for example, here is a web server contained as a service. So this is the httpd.service forking a number of web servers in the foreground here. And here is the system getty slice, which of course is the getty service, the firewall service, and you get the idea of what this does. If we do systemd cgtop, you can see exactly what I said earlier on in the slides. So you see all the different slices and the processes that they have, the number of tasks that they have, the percent of the CPU they occupy, the memory, and the input-output per second. Okay, let's move on to actually demonstrate how to run a transient process with systemd. Okay, in order to run a transient process, something that's not started by a permanent unit file, we still have to invoke systemd, and the command is systemd-run. We give it a unit, a transient unit name, and then we give it a slice name under which the process hierarchy should appear. So essentially what I'm going to do here is choose a common command like top -b to run top in batch mode, and then place it under the system process hierarchy so that we can actually see it, start it, and stop it with systemd. So let's go ahead and do systemd-run. The unit should be something like top test, and the slice should be something like georgios.slice. So I could actually put that under the system slice or any other slice in the system, but for the purposes of making the illustration of this transient command easier, I choose to make my own slice called georgios.slice. And then, of course, the command, which should be the very last thing, is top -b. If I do that, then I get a confirmation running as unit toptest.service. So if I now do systemctl status and then pass it the slice, I could actually see that there is a process. In this particular case, PID 5417, and there is my top -b running there. If I want to display the process hierarchy again, I would do systemd-cgls, and under the very top slice here, georgios.slice, I see a service called top test service, and then under this service I actually see the /bin/top command running. So pretty much I can do whatever I want with this service. Right now I can, for example, go and do systemctl stop top test.service, and then do a status to verify that this status has that the actual service has stopped, and actually start it again. But as you can see, this is actually a transient process. We don't have a permanent file, so essentially this process, since it stopped, it has now disappeared from the system. I could try and do something like this. And yet, as you can see, there's nothing I can do to bring back that process. Okay, so essentially this process has now disappeared since it was a transient process. In the next example, we're going to see how to actually make a proper unit file to start a proper service and apply resource limits to it. Okay, let's proceed now to the last demo of this video, which is a demonstration of how to make a service and apply a cgroup limit to it. So what we're going to do, we are going to make our own service and place its unit target file under the user lib systemd system directory. Then we're going to reload systemd in an attempt to load the unit file, attempt to start and stop the service, and see that if everything goes well, then demonstrate the very essence of a cgroup administration, which is how to apply, in this particular case, a memory limit to that service and see it taking effect. So let's go to the system and let's navigate to my home directory on this system. Here we can see two files. One of them, which is a single executable shell file. And what it does, it calls periodically every 2 seconds the memhog program. The memhog application is a simple application where, for example, it hogs the memory, and it actually sends some test patterns, and it occupies the memory. It's useful for some system tests and some for the purposes of stress testing the system. But what we do in this particular case, we memhog a 2 GB RAM memory chunk, we sleep for 2 seconds, and then we do the same thing over and over again. So that's going to be our small test service. And then let's have a look at the second file, which is the actual unit file. This is what a basic unit file looks like. So you have the unit, service, and install entries. Under the unit section, you have a basic description. In the service section, which is the most essential one, you have the exec start and exec stop directives, essentially instructing system B what to execute to start and stop the application. And then this is the target, or in the previous life of system V, the run level dependency. Here in this particular system, we are executing this under the multi-user.target, or what used to be known as run level 3. So let's go ahead and actually perform the first step and actually copy the memhog test.service file under user lib systemd system. There was a previous incarnation of that service there, so that's what I would do typically on the first time. So going under that directory now and actually checking that everything is okay. Let's see, memhog, and yes, we are here. At that point, let's try to reload systemd in an attempt to force the systemd daemon to reload all the config files, the unit files. And then the next thing we should do is systemctl status memhog test.service. And here we can actually see that the memhog service is loaded, which means that systemd has successfully parsed the unit file, but is actually very inactive because we haven't started it. So I can go ahead and do systemctl enable memhog test.service. This command should actually start it automatically so that it's like a proper service every time the system boots. And then this command, systemctl start memhog test.service, should actually attempt to start the service. And after clearing the screen, what we can do is systemctl status memhog test service. And as you can see, this is the journal entry here, and essentially we have now started under the system slice a memhog test.service that actually runs in the background, and it's actually executing. Now we can do a systemctl stop memhog test.service, and then again do a status, and again we see here that the service was stopped properly. In that particular case now, we are confident that we have a service that is installed properly, so it was loaded and starts and stops properly. what we need to do now is to actually demonstrate how we can start applying resource limits to this process and service. So under normal circumstances, every execution cycle of the memhod test service, if you remember the script, should actually give us something like a 2 gig RAM chunk. So let's say that we don't want that and we need to actually execute something or apply something that will limit the amount of memory to 1.2 gigs. To do that, we will need to apply the systemctl set property command. And let's say that we want to make this change on the runtime process. I'll explain what this means in a minute. The memhog test.service is the service that we are actually interested in limiting, and we will apply in this particular case a memory limit of 1200 megs, which is a little bit under 1.2 gigs. So if we do that, we can actually not see anything happening yet, but what we have done here is we said to systemctl, go to the memhog test service and apply at runtime this particular memory limit here. The dash runtime switch, what it does, it applies this limit temporarily. In other words, if I go now and reboot the system, and the system will of course automatically restart the memhog test.service, this limit will not be in effect because it was not written on a file and it was not made permanent. So if I now attempt to actually start the service again, so we do a systemctl start memhog test.service, and I do a status, I actually see that the systemctl daemon reload is recommended here. So I'm gonna go ahead and do that, because every time we change limits, these limits need to become effective in systemd. So let's try and stop and start again the memhog test.service and status, and this particular memory service is actually running at the moment. Let me clear the screen now because we had too much information. But if we wait a bit and then do again a systemctl status memhog test.service, we're going to see that eventually the service fails to start, because the reason it fails to start is that now it tries to acquire more memory than the 1.2 gigabyte limit that we have just placed. So that in effect demonstrates very easily how one can actually create a hierarchy of processes and apply a memory limit. So this is something that you can typically do with a Linux control group. Thanks for watching.